Alright, we're here with objective 113. Students will be able to reduce fractions using prime factorization. Okay? So why do we even need GCF or factors for that reason? In Algebra 1, the biggest application we have is to simplify expressions. And we'll use this concept again and again to do just that. Our main focus today is going to be, and it's even in your objective, to reduce fractions. Because that is one way we can simplify an expression. If you look right here, we'd really love if you just pause the video for a second and try to think logically about how all of these are going to simplify. I'm going to walk you through it now, so you make that choice on your own. Right here we have 5 divided by 5. A lot of students say, well, 5 over 5, or like 5 over top 5. It's really important to be aware of what operations involved there. A fraction is telling you to divide. So this is saying 5 divided by 5, which we know is a 1. Same logic for B. 7 divided by 7 is 1. 8 divided by 8 is 1. And you can probably see a pattern developing. -4 divided by -4 is 1. You could also think of like 2 negatives divided. There's going to be a positive, and then 4 divided by 4 is just 1. Now we get into a little more abstract idea. If we have x divided by x, that also equals 1. Some students here like to put x, which like, we can understand that, like there are a bunch of x's, like why wouldn't it be x? But think logically, if x is just a variable, we know a variable represents any number. What if x were like 7? Actually, let's pick the other head. What if x were 9? So let's plug in 9 for both those values. You have 9 divided by 9. That also equals 1. You had -50. -50 divided by -50 equals 1. So regardless of what you plug in, if it's the same value, it's going to come out to 1 when you divide those two. And last one, just for fun, a smiley face divided by a smiley face also equals 1. It's not more smiley faces. It should be, but it's just mathematically it's not. Okay? So a big conclusion you should be able to draw from this is any number divided by itself equals 1. Yes, Ms. Hyder.
Does it have to be a number, or can it be a value like a variable?
Interesting. So what if we had like y divided by y?
Yes.
Like, would that always be 1?
Yes.
So I hope you can answer this now. If not, I will walk you through it again. Looking at e, that's kind of the same logic we used. If we had any value divided by itself, we're going to get 1. If you had any decimal divided by itself, any value at all divided by itself is going to give you 1.
So one thing to be aware of, when we are canceling a numerator and a denominator, we have to be sure that we are only canceling out factors and not expressions with addition and subtraction. For example, if we have 3x, since they're sitting next to each other, we should know that that implies multiplication. So I can rewrite that as 3 times x. Now if I put this over x, we have x over x, and we actually can cancel that out because it becomes 1. So 3 times 1 is just simply 3, so we leave it there. If you had 3 plus x over x, notice this addition sign makes it so it's no longer a factor because there is not multiplication there. So I cannot cancel these because these two are not factors, and you can only cancel out factors. To prove this a little more, I'm going to rewrite these two expressions. Make sure you get this down. Okay, if we cancel this, we should be getting 3. So technically, if we have if we have x equals 2, by substitution, we should have 3 times 2 over x, which is 2. 3 times 2 is 6, divided by 2, and we get 3, which works out, because again, these were factors. However, if you have 3 plus x over x, we cannot cancel it and get 3 because we're not actually going to get 3. So given that x equals 2, by substitution again, we would have 3 plus 2 over 2, giving us 3 plus 2 is 5 over 2, which is 2.5, or 5 over 2, or 2.5, however you want to look at it. But it is not 3, and therefore we cannot simply cancel here.
Alright, so we're just going to show you maybe 1 or 2 examples of how you can use this. Let's look right here at use common factors to reduce 9 12s or 9 over 12. What a lot of you should do, because I know you've done this before in middle school, is just think what number can divide into 9 and 12, what's a factor of both. And I hope a lot of you came up with 3. If we're trying to reduce 9 12ths, we can just divide top and bottom by 3. We get 3 fourths. Now what's really cool is we can do that exact same thing with prime factorization. Let's say I have 9 here and 12. I could prime factorize 9. Get 3 and 3, both those are prime, so we're done. 3 and 4. I could break down 4 into 2 and 2. And now I'm going to rewrite this original fraction as a product of its prime factors. So if I have 9 12ths, that equals 3 times 3, and then 2 times 2 times 3. Since these are multiplying, they can easily cancel. And I'm left with 3, and then 2 times 2 is 4. So I still get 3 fourths. Notice how we have divided the space over here to do that. So if I write the prime factorization of 9, 3 times 3, then I have 2 times 2 times 3. The 3's cancel, and you're left with 3 over 4. Now we don't have to use up all this space for the problem. What's really helpful with all of this is once you get into really big fractions, using the prime factorization method will make it a lot easier. So let's say we had 102 over 150. What a lot of students do is they look and say, okay, these are both even, so I'll divide by 2 and just keep dividing by 2. That's fine. That'll definitely work if you're consistent. But it's going to take a lot of time. If you prime factorize both those values and find what common prime factors they have, you can save yourself a lot of time. So if I have 102, 2 and 51, and 3 and 17, I have 150, 2 and 75, 5 and 15, then 5 and 3. I'm going to now rewrite these as a product of the prime factors. So I have 2 times 3 times 17. I'm going to have 2 times 3 times 5 times 5. If I cancel these out, then I'm left with, I'm going to erase this just so I can write the final answer. I'm left with 17 divided by 25. And ideally, this is a lot more accurate, and it should save you time with these really big fractions. A great way to check to make sure that you didn't make any mistakes, again, the prime factors that you found, they have to multiply back to the original value. So it's a good idea just to check to make sure when I multiply these together, do I get back to the original value I was trying to find the prime factors for? Go ahead and finish the rest of this page, and finish the page 17 on your own for the rest of this objective, and we'll see you in class next time.